So the problem with thinking about, we call the first definition, or the part B, we call that pointwise continuity. When we go to our next class, or real analysis class at the graduate level, we stop calling it continuous and call it pointwise continuity, because it actually means something different than, because you're looking at it point by point. You're taking it x equals c and saying it's continuous at that particular c. And then it satisfies this definition of continuity at that particular c. So point by point, you're saying it's continuous. There's no gap in the action. There's no break in the action at a very specific point. So that's why we refer to the other definition, the definition B, as pointwise continuity. This is a similar concept. I'm going to show you. It's kind of strange. It'll be something new, but it'll give you an idea of the issues with looking at functions point by point. Eventually, you want to go to a place where you're dealing with sequences of functions. And all the math that you learn in this class should pull up to sequences where you think of the function itself as being a vector. So the way the progression of this class should go is you first you work on R, you do integration, and then you go to, just like calculus, go to multi-dimensions. So you go to Rn. And you have the machinery of linear algebra that gears you up to get ready for working with Rn. And then the whole point, I think, is that Rn is like R in so many ways. Instead of absolute value, I have magnitude. So I have a way to talk about distance between vectors, where before I had distance between points. And some of the math doesn't transfer over. And so you get hung up in your linear algebra class of places it doesn't carry over. And also in 255, 205, those courses, you get hung up on these things that don't actually pull over. But I actually wish that when you took those courses, that someone told you that Green's theorem and Stokes' theorem are just integration by parts in multidimensions. So you can see that transfer, that you're actually just taking what you already learned in calculus and then extending it to multidimensions. You want those same machineries and tools that you had back in Calc 1 and apply it to something in typical university, we call it Calc 3, but 255 or 205 here. So that's what you want. So what I really want is I want to gather up all these continuous functions. Let's make a domain that's 0, 1, the closed interval. And I want them to be put into a set. And I want that set to be a vector space. Because then I can start talking about things from that you learn in linear algebra. And I also want the same ideas that I had, like from Rn, I had magnitude. I want some way to talk about size of functions and distance between functions. Because if I had that, then I could talk about sequences of functions. And all this stuff that you're learning here would carry over. So I want something like that. Because that's what mathematicians do. We abstract things. I remember I was giving a talk. I helped a lot of folks in the EE department in the master's level because they had to take this course as a requirement for their master's degree. And this course is not fun for an electrical engineer. And so they eventually invited me to give a talk in their department. And I kept talking about points in a space. And they're like, you don't have a point. You have an infinite sequence. Like the whole sequence is a point. Because I'm thinking of these kind of abstractions. But it was so foreign to them to think about it. But that's eventually, I think I was third year of grad school. I was thinking that way already, that this is just an abstraction of stuff I've already learned. So let me propose this one to you. Well, the first thing of size and distance, I could say two functions are far apart from each other if I just point by point look at the distance between them. This becomes a really attractive idea initially, but it's a really bad idea. Because one of the things I want in a good space, a good vector space with a good distance, is I want all Cauchy sequences to converge. Because I need that. For a lot of the theorems that you have in this class, I need Cauchy sequences to converge. And it's not going to work out for this, for a pointwise definition like this. And I can show you a quick example. Let's take these sequence of functions, x to the n. Plot them on decimals. All of your computers, open your computers and plot. Constrain it to the interval 0, 1, and then plot them on decimals and let n get higher and higher. Tell me what you see. And I really want everyone to do it. Because I'm Thomas for a reason. You've got to see to believe.
We plot like multiple on.
Yeah, plot like take a n equals 1, n equals 5, n equals 10, and you'll see what's happening. You have to do it on 0, 1. Otherwise, if you go outside of that range or outside that domain, it's not going to look right. I can help you with y equals x. Here's y equals x. What are you getting, Alex? Oh.
It's the animation plays, and now I have some lines in.
Right. So what are you getting? What are you getting for smaller ends?
It looks a lot like well, negative ends or like close to
Let's
zero.
say this is one of yours. Like you can say like this. What happens when n gets larger?
That gets steeper.
Steeper how?
It's wider for longer, and then goes
Okay, so it's doing that.
sharper increase. So I guess as n approaches infinity, you're approaching a right angle.
There you go. That's a nice picture. You should be getting that. And I asked you to do it yourself so you can actually see like when you increase n, it's getting flatter and flatter down here. So point-wise, where do you think it's converging to? What do you think it's converging to? Point by point. Like if I picked a point here, right there, where as n goes to infinity, where will n of x go?
0. That's all right. Yes. It's one step. Yeah. So
Step function, I don't think it's exactly a step function, but it's what we call jump discontinuity, right? What's going to happen? What's the problem? Like it's going to go flatter and flatter and flatter like you have it. Like the next one, maybe you can make it go like this, right? But where is it hinged? What about this point right here? What's this like f at 1 converging to?
1.
Well, where's f at 1 converging to? 1. So it's like that. So it's not exactly a step function, it's just a jump discontinuity, right? So flat, it doesn't like, step means that you have stairs. So if you look at that, this is unattractive in the same way that the rationals are unattractive, because you can create a sequence of rational numbers that converge to something that's not a rational number. And in fact, we say that the rational number is not complete. It doesn't contain all its limits. If I use this definition for size and distance, the pointwise definition, it's unattractive because I can generate a sequence of continuous functions that converges to something that's not continuous. Let me say pointwise. Right. So this notion of distance pointwise is bad in other ways, but you can already see it's unattractive for pulling the data we have in this class up to this level, where we think of each function as being a vector in a vector space. And they are, because you study that in linear algebra. At some point, they told you continuous functions form a vector space. They definitely told you polynomials form a vector space. But this is unattractive for limits because you don't want to limit out of the space. Then all Cauchy sequences don't converge and everything else falls apart.
I have a sneaking feeling that space means a lot more than we think it means right now. What is
vector space? So you have I'm not going to go through and write them all down, but recall that the scalar multiples of a vector remain in the set for subspace, and the sum of two vectors remain in the set. But then for our definition of vector space, you had 8 total properties. You had an identity. Yeah, so I don't want to list them all up here, but it's in your David Ley book, and I believe it's even in the what's that other book that they use, Gilbert Strength. It's in that one too. They have to. They have to have that definition. So your math that you learned in linear algebra, it's called algebra for a reason. You're using abstract algebra, and you're using this notion of something called a vector space, which has properties of commuting and a distributive law with scalars, and you worked over a field. They'll even say over a scalar field. Like the book Strang probably says that. I'm not sure if David Ley says that. But the field in your case is, but we're going to take the field to be the real numbers all the time. So this is unattractive anyways because you don't have all the Cauchy sequences converge. And so the way to do distance so it works is what we call the uniform norm. Let me put 0, 1 if he doesn't make it any set. Let's take the soup of that difference. We also call this the soup norm. The magnitude that you use in vector spaces, x1 minus y1 quantity squared plus x2 minus y2 quantity squared square root. That one also satisfies the state properties as absolute value. So if you do this, it also satisfies the properties of absolute value. That means it does all this kind of same things that absolute value does, which is kind of cool. So the theorems that you prove with absolute value metrics works here as well for this guy. And now this guy changes.
Sorry, what is that called?
Soup norm.
Soup norm. This uniform norm, also known as the soup norm.
Yep. And I brought it up because we want to preserve that property right now. And if you look at that, the soup norm of this any one of these FNs is going to be 1. We did some of these topology.
Take any two colors going into existence, shed is always going to be 1.
Yep. Isn't that nice? They convert us to 1 in the soup norm.
It's kind of weird, but it's there. Right?
It works, and the thing is, you use this, and why electrical engineers have to take real analysis is you use this for Fourier transforms. When you're doing a Fourier transform, you're acting on a function. Laplace transforms, you're acting on a function. So you need to work over function spaces. So you need stuff like this, the machinery for this. They don't feel so. They're taking it the first year of the master's program, but they do need it. They do need to understand what works and what doesn't work. So that's how this works. And I mentioned this, even though it's not quite the same as uniform continuity, to give you an idea, like you're really taking soups over sets so that you have one delta to rule them all. It's easier to see in an example like this why that works, why it's important, why you need this uniform property. But that's why you need the uniform property, because things work out in the way that you want it to and need it to do real analysis on top of continuous functions. That's why. So I asked you next question. I don't expect you to answer it, but think it over and then see if you can come up with an answer to the next question, which is, what if I have a continuous bounded function? You gave me examples off the fly of things that are not bounded, like x squared. You also gave me 1 over x. I think Dr. Moen probably gave you that. Is it true, like if I take a nice function all over R, it's bounded all the way through R, is that going to be uniformly continuous?